Aimee Price, giving a nice talk on SEM imaging, low KV, more focused on looking at the material side of things and on the microscope. So she'll have some nice insights to look at that. Aimee is our next door neighbor over at Nanotech. She's the manager for the lithography systems over there. So like with that, I know she's involved with a lot of STEM outreach and also is meeting for advanced electron lithography, kind of stuff. She's also a fellow Penn State graduate, so I always appreciate that.
We are. Hey, how are you?
Okay. Hey.
Thanks, Dan. Thank you to everyone who's here in person. It's really nice to be in person with people again. And thanks to everyone who's online. Dan, is the camera there? Is that
that's
okay?
Camera.
I want to make sure I'm not like staring at my computer. I'm a wanderer, so I'll wander a little bit. So thanks, Dan, for the invite. It's really fun to come down here. I've never actually been on this side of the digital theater, so appreciate that. Like Dan said, my name is Aimee Price. I am the manager for nanofabrication here at Ohio State for the Institute for Materials Research at Nanotech West Lab, which means that I manage the clean room user facility here at Ohio State. So as part of that, we have, I'll go through a little bit about Nanotech West, my Nanotech West commercial in the next slide. But a part of that is we have lots of open use user equipment, just like CEMAS, but we have about 55 pieces of user equipment in the clean room. And so we have electron microscopy and optical microscopy, as well as other metrology tools and analytical tools that we use as tools to evaluate our processes that we use to create devices and the fabrication side of things. And we also use those to evaluate devices. So we are basically fabrication scientists and engineers that are using microscopy as a tool to evaluate our processes and our devices, rather than microscopists that are using tools to advance the field of microscopy. So my talk today will be focused on that, basically on the applications for electron microscopy in a nanofab or a fabrication environment, more on the research side of things than on a production side, but we can talk about that a little bit. So I'll go through a lot of applications about why we use electron microscopy and specifically why we use low KV SEM. So my co-authors here are Dave Hollingshead and Kavya Dakatreya. Both of them are actually also engineers over at Nanotech West, do a lot of the fabrication and also quite a few of the images that you'll see as well. Oh, let's see if I can post this. Here we go. So a little quick commercial about Nanotech West. Like Dan said, we're their neighbors, CEMAS's neighbors to the west. We're only about, I don't know, whatever, 75 yards west of here. And we are an open use user facility. So the whole facility has multiple laboratories in it, the biggest of which is the clean room or the nanofab. We have about 300, 350 users every year. We do not belong to one specific department. So we fall under the Office of Research through the Institute for Materials Research and Manufacturing. So it's very by nature, interdisciplinary, cross-college. We also have many, many users that are external to Ohio State, both academic and industry, and a few government labs as well. What I'm going to focus on today is our semiconductor fabrication side of things. We've been doing this. So Nanotech West was previously Ohio Micro MD Laboratory. We've been around since 2001 and serving the Ohio State community. There's obviously a very large renewed interest in semiconductors and semiconductor device fab here in the state of Ohio with the news of Intel, their new fab being built about 30 miles to our east. So what we are is a research facility. We serve about 100 to 125 new users every year. Like I mentioned before, we have about 50 tools, 50 plus tools. We operate on 4-inch or 100 millimeter and smaller, mostly smaller. Ohio State is a very materials-driven community, as most of you are aware. So we're looking at advanced materials devices on advanced materials. And so a lot of times that's not wafer size, that's centimeter size and smaller. A lot of what we do is compound semiconductors. So not silicon. So we're not Silicon Valley West. We do a lot of compound semiconductor materials. And then just for the electron microscopy folks, so we have trained since its installation about 300 users on our Zeiss Ultra Plus SEM, which is located in the clean room, about 50 per year. So again, these are not microscopists. These are people who are using the microscopes as a tool to evaluate their processes, their fabrication, and in some cases, their devices. I'm gonna kind of skip through the other ones, but we also have a significant endeavor in energy storage. We have battery research, battery innovation going on, and there's also a medical modeling facility in Nanotech West. Okay, so quickly, some of the things that I'll talk about today and why we use low kV SEM. I'm a nano person. My expertise background is electron beam lithography, so nano patterning, nanolithography. And so we do look at nanostructures. These aren't going to be impressive to the CEMAS community when you guys are looking at atom scale resolution, but this is the type of materials that we're looking at on the nanoscale. So these features are around 20 nanometers. We'll talk about exactly what they are later. But these are the types of applications that we use SEM for. So we are a user facility of equipment, right? So we're constantly installing, qualifying new equipment. Dan was just telling me about, an upgrade here to one of your instruments. And so you're always having to keep state of the art and add new equipment, and how we actually do that depends on the tool. But in the case of our lithography tools, we need to be able to evaluate them. We do that with SEM. This is vernier structures. So we're looking at alignment, accuracy, from one layer to the next. So aligning two layers, overlaying them on top of one another, and actually checking to see how well we do that. This was an alignment test during qualification for our direct bright laser tool. And so basically what you're looking at here is the two sets of lines will line up perfectly where the alignment or misalignment is. So this one I think is about a plus 0.3. You can actually see it here. I think you can see it, where they're actually lined up 1 for 1. So any shift the other direction, one way or the other, those verniers will not actually line up. And so the tool is much better than that now, but this was during the installation. So something that we can't quite see in an optical microscope. We use this for resolution checks. So this is one of our old lithography tools. And I'll note later that this image was taken at 0.7 kV, so 700 volts. Really the heart and soul of what we use SEM for in our lab is for process development and troubleshooting. This is a work done by Professor Daniel Gallego-Perez and his group. He's in surgery jointly with BME, and they're doing basically drug delivery therapeutics on the nano and micro scale. And they're looking at basically their process, how well these materials are open. These are actually nano channels. They're one side of a device that open to another side that's on the micro scale. So they're looking at these in cross section. And we do look at right? Tools don't always work as they are designed. This is a lot of what we do as well. So we're troubleshooting, right? We'll talk about this particular application. But these two images are from the same tool in the same shot. And they're supposed to be the same, and they're not. But looking at these plan view on an optical microscope, we could tell something was wrong. In fact, you could tell macroscopically that something was wrong, but you could not tell until you were in a cross section with the SEM what was actually going on. And then we look at obviously novel devices. We do new research, so we're looking at novel devices and fabrication techniques. And for us, for low voltage, we actually need to look at surfaces in their native state. You can see I have some contamination on this image, but we're looking at semiconductor materials in their native state, so we can actually look at their morphology and cleanliness as we're processing, but also as they're actually grown and created from in our epitaxy labs. Okay, so why locating? Why are we here? Started to mention this in the last slide, but we want to image the native semiconductor surfaces and the thin films that we create, we deposit and or etch without coating them. In many cases, it's absolutely critical that we do that, but that's really the driving factor, and the rest of these sort of come along with it. We also want to be able to inspect for thin contamination or residue, right, that otherwise might get lost in the fact that we're getting most of our signal from the bulk of the sample. As you all know, we do it to minimize charging without coating it. Also, it's specifically to some of our polymeric materials, we want to minimize electron damage. And our photoresists, what we'll talk about a little bit, have some significant shrinking under the electron beam that can change the measurements and also the size, the shape, and profile that we really care about. So it's really important to us that we minimize that. It's not always possible to eliminate it, but it's important to minimize that. So in the semiconductor production facilities, they'll have CD, critical dimension SEMs, CD SEMs. And this is one of the major issues for them, right? They need to make sure that when they're taking their measurements, they're not actually altering the measurement while they're doing that. So it's something that's really critical. We don't have a CD SEM, just the nature of our lab. But in the semiconductor sort of manufacturing world, that's something you'll hear a lot about. As most of you know, low voltage, higher surface sensitivity. We have a Zeiss Ultra Plus scanning electron microscope, and it also has, so like you guys have like a TLD detector. So our version of that, the Zeiss's version of that, sort of operates a little bit differently. It's called the in-lens detector. It's very surface sensitive. Fundamentally, so we can also use that at higher voltages if we chose to, but in general, we get higher surface sensitivity with lower voltage. So I really like this image from Zeiss. Here on the bottom, you can see they went from 200 volts up to 15 kV. That's the only thing they changed, and you can see the difference in the surface sensitivity based on just on the electron interaction volume, right? And for us, we don't want to coat it because we want to continue processing and continue fabricating on that particular specimen, that sample, after we've imaged it. And you can remove coatings, of course, but it's not exactly the cleanest process, and we want to be able to do that without coating and stripping. So this one I might come back to. This is not the best. This is one of my training samples. Actually, it's very dirty. As you can see, this is a gold on silicon. And so this is just a comparison for students when I'm talking about, hey, why would you use the Everhart Thornley versus why would you use the in-lens detector? This isn't at super high voltage, it's at 5 kV. But you can see the residues are visible here on this image in that you're not actually able to see on the SE2 image. So partly there's a slight difference in brightness, but also really it's the detector here. So I wanted to make note of that because we actually do this quite often at 10 kV, just because it's a good training mechanism. Okay, so let's talk about some of the things that we actually use this for. So again, I talk about resolution tests. So as a lithographer, lithographers basically we're patterning on a useful substrate, and we do that by coating something that is sensitive to photons or sensitive to electrons. And then we transfer that onto a polymer material. And then that mask, that polymer mask that we've created, then gets transferred into a useful substrate. But we need to be able to actually qualify, test, verify our tools and our equipment as well as our processes. And so this was an I-line stepper. Basically takes an image or a mask file, or CAD file that's we call a reticle. And then we reproduce that 5 times reduced across a wafer. So it's stepped across the wafer. And so we got this as it was a donation, right? So it was a free piece of equipment. Free pieces of equipment are never free from the Air Force Research Labs. And so we had to evaluate it before we put it into processing in our lab. So this was, these images were taken a very long time ago by an engineer who has moved on to the medical center. And we wanted to image these as developed. So these are taken at 700 volts. And we were looking down at the resolution, the whole resolution of the tool, but also across a wafer and across a flash, across a shot. And so in this case, we're about 600 nanometers. You can see some of these little pillars are slightly smaller than that. There's some features in there that we won't talk about today, but there's some features in there that are very interesting that have to do with reflections that you can't see with an optical microscope. You can only see in cross-section, and they're very important to the lithographers and to the process. We use these for higher resolution lithography. So I'm an electron beam lithographer by background, and we want to actually, push that resolution so we can make smaller and smaller devices. So we use that a lot to look at we have no other way of doing this. That what I used to have to do before we had an electron microscope was go to CEMAS, before they were CEMAS. And so the problem with that is you expose, you develop, you've got your sample, then you wait, you take it out of the clean room, you do something, you come back in. So this was actually one of the major reasons that we had to have an electron microscope in the lab, because we were able to produce something, but we couldn't evaluate it. It was too small for any of the techniques that we had. So in this case, we were looking at, I picked this example for several reasons. The resolution isn't super high. It's not very small features. But we are looking at a quartz substrate. It's about 1/4 of an inch thick. It has another dielectric on top of it, tantalum pentoxide. It was fused silica. So fused silica with tantalum pentoxide, and then SU8, which is actually an epoxy. It basically is an epoxy resist that you cure with the electron beam when you expose it. So we have insulator on insulator on insulator. And this project was really important that we know the morphology of the surface, because it was for an optical grading for a low temperature atomic physics project. And they were trying to make grading couplers. And the surface roughness and cleanliness was really important. So we had to be able to image it and know what we were doing as we processed. So we did that with AFM, gives you some of an idea of what's going on. But we actually use this as a test bed for this microscope. And what you're looking at here, the lines are SU8, cured lines by the electron beam. They're not the prettiest things I've ever fabricated, but they are pretty small. But you can see in the middle is the morphology of the tantalum pentoxide, right? So that's really important for us to know what that looks like. And if you can kind of see, I have my glasses off. It's a little bit more difficult to see, but there are some scratches, some lines kind of diagonally. Can you see those on the screen, maybe? They're actually in the substrate. So all of this would be lost, right, if we coated it. It would also be lost at higher voltages. So this is one of the examples that I always use when we talk about low kV in our facility and why we need it. So this is just a quick overview of a process. So one of the things that we do all the time is look at our process, and that means to us as our recipe, right? For anything we're trying to do, what is the recipe, what is the process, and what does that look like from start to finish? One of the most important processes that we have is called lift-off. What does that mean? It basically means that we're adding a material in specific areas to a sample, to a substrate. And so we're masking areas that we don't want that material. So in this case, it's gold or metal. We're masking that with photoresist. And then the goal is to leave that metal only where we want. And that sounds really simple. And it is really simple, but it's not always trivial. So what you've seen here is basically we coat this with a photoresist. We pattern an area, this big square. In this case, well, we pattern everything but the square. We leave this area that we're masking. We do a blanket coating of metal. So in this case, we take it in a vacuum chamber. We evaporate metal onto it. Metal sticks everywhere, hopefully. Metal sticks everywhere, hopefully. And then we put this whole thing into a, oops, we put this whole thing into a solvent, and we dissolve the masking area. It's just a sacrificial layer. We spend a lot of time and effort on the sacrificial layer. So that gets removed and hopefully takes the metal that's on top of it with it. It sounds really straightforward. We're left with the pattern we want. We move on to the next step of the process. That's ideal. And this is up in the corner here is an example, I think, of a solar cell. And that's what we hope works. That's not always the case. So sometimes you end up with a mess. It doesn't lift off. You have metal everywhere. Sometimes the whole thing comes off. Why, right? And that's what we need to understand. So ideally, we want to see a resist profile. I showed you kind of a schematic of that. But what we want to see is what we call a reentrant or a negative resist profile. And the reason for that is in this slide. So this top image is of a cross-section of one of our photoresists that has that nice negative profile. And then what we're showing you here is this is what we were looking for, right? We want this undercut of the top to the bottom. And the reason for that is in the next part of the schematic here. So we put that metal down and it's pretty much line of sight. And so we're depositing that. There's a little bit of angle to it. So that metal sticks everywhere. With the reentrant profile, you get a break in that metal film or that dielectric film, which is even worse with dielectrics, right? So we have this nice break here. That's physically a break in the film, and that leaves access for the solvent to actually get in there and lift it off, right? If you have a continuous metal layer covering the film, how do you get the solvent in? Well, you have to physically do something, and that can cause all kinds of problems, damage, pulls it off, things like that. So this is an example of, okay, this is a great profile. This is the result of that profile. This is silver, about a micron of silver on silicon, a little bit less. And so everything worked pretty well. But that's ideally, right? It doesn't always work that way. So we need to know, okay, this resist and this substrate, this exposure tool, this developer, what actually is the result. So these are the options. And you get all sorts of weird things. You can get things with like wine glasses. You can get, I'll show you in a minute, sometimes they're off center. But we can get this nice negative reentrant profile, which I showed you in the last slide. You can see this one's charging. Even at, I think, let's see, what am I at? 3 kV, that's our typical 3 kV, it's charging, but we didn't code it. The one in the middle is straight. So these are actually beautiful profile, just not the lift off. And the one on the right, or my right, is the opposite, is a positive slope. And so this actually is more common that you can get out of your process, and it can be a massive issue, right? In this case, you could cover that whole thing with your deposited film, and then you might never get it off. So these are kind of the options. And one of the things that we want to do with liftoff is create, we saw one of those things, you can make metal pads, you can make contacts to those, you can do other things. One of the things we want to do is make solder bumps. So if you have a device like a detector, and you have to be able to control that detector with an integrated circuit, so a readout integrated circuit that controls basically the logic to run that detector. There are two separate devices, they're two separate chips, and you need to put those together somehow. One of the ways that you do that is you make these bumps that look like this out of indium. So you deposit the indium and you reflow them. Indium's very cool, wants to bead up and make these beautiful uniform bumps. But you have to lift it off first. And it's very soft, and it wants to go all over the place. In fact, it does go all over the place. So this is the goal. And we had a devil of a time doing this. So we have this, I just talked to you about, it's ideal. We want a negative reentrant profile. We have that. We have the images of it. And then we would see like all sorts of weird things after the liftoff. We would get residue and we have problems with shorting or whatever, just with this at this step. And we said, okay, well, let's go back and look at the profile. So we did that and looked beautiful. And then we did it after we put the metal on. So this image on the left here is actually with indium. And you can see it's very, we got a thick layer of metal. We have this nice ideal profile, right? But if you look very carefully, you can see that there's metal, very thin metal on the sidewalls. And that's just the nature of the deposition tool and the metal and the temperature and all that good stuff. So non-ideal, even with the ideal profile. And you can continue to make it more and more negative, and eventually things fall over, right? So we tried many different techniques to do that. The good news was it still lifts off. We have some residue in here, but the nature of indium is it likes itself, right? So when you do this reflow process and make that bump, the good news is as long as you pretty much have it right, you end up with these nice uniform bumps that you got here. So it's important for us to know what's going on. And I have hundreds of images of experiments that we tried to change the profile, change the deposition, change the temperature. Should we switch to a different type of tool? The answer to that is probably yes. But we didn't because we didn't have to. So this is an important lesson for us that, as much as we want it to be as ideal as possible on the fab side, the important thing is the device. In this case, the device work. Okay, so that's process troubleshooting or process qualification. This is tool troubleshooting. So we talk a lot about profiles. So we're going to spend a little more time on profiles and other things today, because this is the kind of thing we care about and we're constantly talking about. And one of the things that we were seeing when we were doing the process development with our brand new direct write laser tool, this was right at the beginning of 2020. So we ended up having to qualify this tool after the shutdown. So we had installed it, things were ready to go. We were shut down for 2 months. We came back and we said, okay, now it's time to actually do the process quals. So let's look at these cross sections. So we did, and we said, oh, that's weird. It looks like it's not symmetric. Well, maybe that's the way so what we do is basically scribe and break. So we cleave, easy, there's no fib, any of that. We just scribe it, break it. We find that actually works really well. But, oh, well, maybe we cleaved it and it wasn't aligned perfectly to the crystal plane. And so maybe it was off. And we end up with this that looks like it's asymmetric, but really it's not. Well, we cleaved again, and we cleaved again, and we looked at a different resist. Nope. Reality is this was real, and this was an exposure issue. So we went back and looked at stuff from the original tool qualification when it was installed, same thing. So, and really the only way for us to see this is with cross-section. And yes, we didn't code it, we could have, you can see it's charging. We were still able to see that. Could we have coded this and still? Yes, absolutely. But this is one of the things that we absolutely need to do cross sections for. And you certainly could do coding in this case, but we choose not to in most cases. So because we're kind of talking about troubleshooting, what do we actually do with that? Well, maybe there's something going on with the resist, or maybe with some of the temperature baking that we do to process the photoresist. So we have a different exposure tool. We use that. So that's what you see on the bottom. Well, that one doesn't have an asymmetry. So sure enough, it was the tool. And what you can see on the right is not the best negative profile, but is the result of basically we had to bring the vendor back in. And this is an optical system. So they had to realign the entire optical system from the laser, basically the mirrors, the DLP basically, and in order to actually project a symmetric laser exposure onto the tool. So now we look for this on a regular basis. Okay, so this goes back to one of the images on my first slide. So if you look at this wafer, you can see that the color is not uniform. So we strive for everything to always be uniform. It should be the same color. If there's color non-uniformity, it means that there's thickness non-uniformity, or it means that there's a problem with the pattern. So we could tell this just from looking at the wafer when it came out by eye. Didn't even need an optical microscope, right? Something is wrong with this picture. And when we looked at it, we said, okay, well, what's going on? And we'll talk about exactly how we looked at that in a minute. But one of the things that's important in this case is these are about 8 micron features in a very thick resist. The resist is about 14 microns thick. So trying to resolve something that's smaller than the thickness can be tricky. This was the tool, the stepper tool that actually flashes. So each of those chips that you see is one die or one exposure of the stepper. And they were big, they were full size, essentially the full size of the die, which basically is pushing the optical system. It's a big lens. So you're starting to get to the edge of the lens and what can actually resolve. What we're seeing is this non-uniformity across the wafer, but it repeats with each die. So one area of the die, one corner looks exactly the same as the one next to it, but it looks very different from the opposite corner of that die. So this is really a question about you guys are electron folks, right? So you understand depth of field, depth of focus. Optical systems, very small. Depth of field, depth of focus are very small in optical systems, and that's what we're fighting here, right? We have 14 micron thick resist, and we're assuming a perfectly flat wafer. And a wafer, yeah, most of the time you get relatively flat, but if you've got junk on the backside or somebody left some dirt or particle or whatever, you could have some issues with flatness. So we're worried about that. Resolution is probably pretty good. The NA of our stepper is 0.4, and our exposure wavelength is I-line 365. So you can kind of do the math, and you can see that we're, you know, in the a few microns of the field. So that's a concern. That's exactly what we saw. So this is, I love this. I actually didn't see this before. I was actually putting this talk together a couple weeks ago, and I came across these images, and I was like, these are amazing. This is one die. This is a cross section from one die, and they're mapped out just like they are on the die, or on each of the die. So you can see basically the upper right is what we're looking for. A bunch of squares, really small. I think they're 2 micron gaps or something, 2 or 4. Pretty small. And they need to be completely open. But look at the one on the upper left. Looks like a bullet, right? A bunch of bullets. That's not going to work for what we're trying to do. And then as we come down, this was charging like crazy because there's still resist in between these patterns where it should be open. And you can see it's just varied all the way around. And this, like I said, repeats across the wafer. So now we see what's going on. You know, why? Like I mentioned, you know, we had to be, this was really only, we actually were able to, with the optical system, just like with the SEMs, right? You can focus on one area, you can focus on another, and it can tell you the difference in height. So we were able to do that until it was really only a 10 or 20 micron difference in the physical height of the sample across this die, which is actually not small, but gave us this non-uniformity. Okay, what's the solution? Well, it's a 40-year-old stepper, so we realigned the optics, we cleaned them, we made sure the wafers were flat, and did the best that we could, and then in the end, had to replace the stepper with a direct ray laser tool. It's just not capable of doing it anymore, if it ever was. Okay, so we may skip this. I'll go through this a little bit. So really, I'm gonna skip this. No, actually, I'll talk about it. So we talked about liftoff. So one of the things that we, you know, the sort of opposite process. So we have additive process. So you deposit something, and then you leave that area that you deposited. The other sort of opposite approach is to etch. So subtractive process. So you put something down, and you etch it, and you leave only the areas that you want that are useful for the device. So we have a couple different ways of doing that. One is with, we call it wet etch. So acid bases, oxidizers, etc. The other is to use plasmas. There's benefits of each. But again, we really care about the profile. I'm always talking about profile, about cross sections. Why do we do that? This is important to us. And the other thing we care about is we're masking areas that we want to actually remain on the device. And that's what the photoresist is. So remember I showed you that really pretty straight profile of resist? This is why you would use something like that. So you want that for an etch process where you don't want it for a liftoff. So there's different resists for different applications. And this is the sort of opposite application. The other thing we care about is if you're etching something, you're probably also etching the mask a little bit. So the selectivity, so how quickly you're etching with the rate of the material versus the rate of the mask is critical, right? Because once you get down and you've used up all of the masking layer, then you start etching and then you change the profile and you change the depth and all that good stuff. So that's part of what we care about. So this little schematic, the etch on the left, the selectivity is awesome. It's 250 to 1. That's great. You very rarely get that. The one on the right is poor selectivity. You etch this at the same rate. So that means you have to have a thicker mask than you would maybe want in order to get the depth of etch that you're trying to do. So that's for the selectivity, but we also care about the profile. So a lot of times what you're trying to do is etch pretty deep. So these etches on the left, this is actually silicon. This is about, they're 50 microns. So they're not the smallest things we've ever made. So the diameter of these circles at the top is about 50 microns. And we're etching 150 to 200 microns down, which is very deep. for the types of stuff we do. This is sort of the opposite side of that biomedical device where they had the nanochannels on one side, and these are the microchannels on the other side, and they're supposed to hook up. And so what we're trying to do here is we want an anisotropic etch, which means that it's etching just in one direction and not the other. So we want to etch down, but not laterally. The one on the right is an example of an isotropic etch. So the one on the left is very much of what we call physical etch. So you're etching with a physical sort of ion, right? You know, you guys are doing gallium cleans, right, on some of your fibs, things that we're etching with the gallium beam. It's essentially the same idea, but we're not we're using the chemistry of the plasma and the physical nature of the plasma to tailor that etch. The one on the right is an isotropic etch, and it's really just all chemistry. You can see you kind of get this UFO structure, and you're undercutting and getting the bowl there. In this case, that's what they wanted. What they're trying to do eventually is make that top surface come up into a needle point, so it can actually penetrate skin, like a skin patch typically. All right, so one of my other favorite examples is this one. This is my work. And again, we need to be able to image things at high resolution at low voltage. So these are 15 to 20 nanometer lines. And then the image on the right is basically, these are HSQ, which is basically SiO2. These are silicon oxide spin-on glasses that you kill with an electron beam, and then creates a really, really high resolution pattern, higher than my current lithography tool can actually do. On the right is, we grew a micron of gallium arsenide on top of the images on the left, and this is the result. And I just included this because I think it's a beautiful image. So you can actually see that it was growing along the 111, right? So we end up with a nice faceted growth, and you can still actually image these 15 nanometer lines at the bottom of a 1 micron growth. So that's pretty much what I wanted to talk about. I want to use some time for a discussion. But basically, I wanted to let you know and basically share why we use low voltage SEM. We use low voltage SEM pretty much every day. In fact, when the tool goes down, a lot of things stop, like today, unfortunately. So we do it for many, many different things. It'd be nice to have more than one, but we can't actually fit more than one. And then CEMAS is right here, so I send my users down here to CEMAS. In fact, we've got some that are in CEMAS and Nanotech West all the time. So we use it for tool, process quals. I talk about cross sections, right? Cross section, cross section, cross section. We do that on a daily basis to look at processes for tool quals, for looking at some of the growth materials that we grow in our epitaxy lab. So constantly looking at cross sections, but also plan view as well. And one of the things I stress when we are looking at new SEMs is that, again, we are not microscopists. Some of us think we're pretty good at microscopy, but we're not microscopists. You're microscopists, right? We need to be able to use the microscope as a tool, and it needs to be simple enough that we can train a wide variety of users that have various backgrounds, right? We have some microscopists, we have some electrical engineers, we have some chemists, we have some geologists, we also have some artists, right? So we need to be able to use this, get useful images without knowing all of the science behind it. Obviously that helps you get better images, but not always necessary in our case. So with that, I want to acknowledge these images and these fabrication processes were done over the course of probably 15 years, and many, many people contribute to all this and continue to on a daily basis. I want to acknowledge Dr. Jeff Marshman at Zeiss, who is one of their applications engineers, who has been absolutely critical in helping us with figuring out the best low voltage processes for us for the different types of applications that we have. So with that, I will open this up to questions, and I thank you for your attention.
Thanks, Aaron.
Sure.
If anyone also online has questions, feel free to post those in the chat. There's a Q&A. If you want to, also you can raise your hand and we can unmute you and hear you in the theater as well. So if you have questions, go ahead, post those, or in the theater, you guys can ask questions as well.
Yeah, one question. You say that when you look at the cross sections, you only cleave the sample.
Yeah. So the question was, when we look at cross sections, we only cleave. Yes, part of that is because we don't have a fib SEM. But part of that is in the case of a lot of what we're doing, it actually works really well because I mean, you do obviously stress the materials as you're cleaving them, and sometimes you can see that. So we have to actually, it's a really good question, actually. We design our patterns when we're doing process development and tool development so that we can do that. So the one where we actually had the small, they're not super small, but the small 8-micron squares, right? We were able to kind of cleave it and sort of tilt it, not get a true cross section. But a lot of times we design something, a test pattern that actually has long lines. So you don't have to be really good at cleaving and hitting your spot, because it can be very challenging when you're trying to like, okay, what's going on with this process? And you have a sample that's this big and you're trying to cleave it and you miss, because then you have to do it again and the sample gets smaller and smaller and smaller and smaller. So if you talk to anybody at Nanotech West, any staff member, they'll tell you that their way of cleaving is the right way. And there are probably 13 different ways of cleaving. So everybody believes that theirs is the right way. And mine's the right way. No. But yes, we do cleave and
That's the only way that you use for the cross section.
most of the time. Yeah, everything that I showed here was from cleaving and breaking. We do have a dicing saw, but that makes a big mess, right? That makes a mess. So you're not going to want to look at something in an SEM after you've taken a saw to it, because all you see is saw marks. If we had a fib SEM, there are probably some different things that we would be able to do. Or if we took the time and effort to come down here and use yours, then yeah, that would probably be a different technique. But sometimes it's tricky because the materials are relatively soft in comparison to the fib, right? So you can smear out some of the transitions if you're not careful with that. And so we just, for ease and cost, that's a good question for sure.
Have you, so often like if I cleave something, I'm not very good at cleaving, but things will just like flake off the surface. You lose a lot of the deposition layers. Do you have ways to kind of help with that?
So yes, a lot of what we're doing, right, the materials are pretty, if the adhesion isn't good enough, then you can definitely have problems with that. And then sometimes at the cleave plane, you'll see it peel back. One of the things that we do that helps with that is coating the surface with like a metal. So a lot of times people are trying to look at thicknesses, like they're calibrating their thicknesses with some other technique. If they're looking at like a dielectric thickness and they want to, we have an optical technique, a reflectometry or an ellipsometry, to actually look at the optical film and the changes in the film to see what the thickness is. But they want to have a second technique to actually compare that to, right? And so a lot of times that's SEM. So the problem with that is now you have a dielectric and a vacuum. So it's tricky. So in that case, what we can do is put, so I say we don't coat, we're not coating the imaging surface, we're coating the top surface that basically gives you an interface. So now you have, you know, your SiO2 or whatever, your semiconductor, and then gold or something on top. So that helps. But yeah, that is a problem. Can be a problem for sure, which is why you would use it.
Aimee, I have a question. In slide 7, you showed the SU8 photoresist pattern, where you are planning to use the grating couplers. So,
This one, yes.
yeah. So I'm just curious, you know, after you develop, then you do the SEM, is it damaging the electric resist in any way or not? Because after that you are etching it or doing the lithotraphy to define the grating couplers.
So the question was, once you're imaging it, are you damaging the resist in any way? First part of the question. Probably yes. SU8, maybe not. SU8 is an epoxy. And so basically when you hit it with the electron beam, you can see, since you've done some electron beam lithography, the dose is really low.
Yeah.
This is so low. We took the photoacid generator out of this. And in fact, I worked with the resist company to do so. And even then, the epoxy just base was so fast, we couldn't really expose it very well. So in this case, this was the final device, not this, but the goal was for SU8 to be the final device. So, you know, if we were using a different resist, and I can't tell you we weren't damaging this, but yes, absolutely. So some of the other electron beam resists that we use, polymethyl methacrylate, plexiglass, just acrylic, is very soft. And so you hit it with an electron beam, you've exposed it, now you are definitely damaging it. Yeah. So In that case, you want to image an area that you don't want to use or a sacrificial sample. Yeah, really good question. Oh yeah, in this case, we were not doing lift-off or edging. That was the surface that we were going to care about. And we ended up using a slightly different process because this is not super smooth. So if you're trying to make gratings,
Yeah.
the line edge roughness on these images is pretty bad.
Yeah.
It's a good example of SEM, but not a great example of gratings.
I was gonna ask, so I've worked with people a little bit semiconductor stuff. And sometimes I've seen people go slightly higher KVs to like go through a layer to reduce the charging. Is that something you try often, like increasing KV? Should I hit that?
We don't, that doesn't mean we shouldn't. We have in the past done ECI on our tool. So we only use higher voltages to do ECI and EDS. Now, neither of those exist on our tool anymore. So we don't. I know we should probably talk about that because as it comes time for us to start thinking about getting a new tool, we need to think about things like that. So I would love to talk more about it, but we do not do that. Mostly because we found a process that works and we're lazy. One of the things that, I guess I shouldn't say lazy, we're being efficient, right? You find something that works, you do that, and then you kind of stick with what you know. But one of the things that's actually really cool with this particular microscope, but I'm sure you guys already knew this as microscopists, I did not know it, was that you can, obviously you can get a whole lecture into charging and positive versus negative charging and how that actually works. But you can step this microscope down by 100 volts at a time. So the cool thing is that you can find that charge neutral point without coating it, without putting anything else into the chamber, flooding it with water, flooding in our case with nitrogen or whatever. So you can actually find that charge neutral point. And the cool thing is that if you're looking at an image like this, where the lines are bright and the background is darker, the contrast actually flips right after you reach that neutral point. So you step right back up or down, depending on which way you came from, and that's your neutral point. So if your sample was charging right after that contrast flips or inverts, then you should be right at the charge balance point. So your charging should minimize or reduce. You probably already knew that. I did not know that until I actually saw it in action, and it's very cool. It's a cool thing to show students, but it requires a lot of patience, right? Depends on how you've mounted the sample itself, how if you put a ground on it, that kind of thing. So Hank's nodding, so I feel better about my explanation.
Do you have good samples for that?
Yeah.
So that's right. Very in my interest.
I can generate them. Yeah, we can generate
like that where you can do that. I've played around with that before. Yeah, it's a pain. You're just like dropping things down. I usually go and use other methods rather than dropping that. But
yes.
I've used times where I've just like slowly gone down and start to see that kind of stuff.
It's very cool.
Like,
we can generate stuff. Yeah, we'd be happy to generate some samples like that. We are not, generally speaking, nobody is patient enough to do that. And so a lot of times when we have a charge compensation, basically a small needle that comes into contact or close to contact with the sample, is essentially like, a higher vacuum version of an ESEM, right? So you're not flooding it with a huge amount of extra pressure with water vapor, but you're using like a very, very thin layer of nitrogen, and you can use the backscattered electrons to actually neutralize the charge that way. Also, nobody really likes to use that either. So people, as much as I like them to try, hey, we have this low voltage. If it gets really bad, people cook stuff. I mean, that's the truth of things.
The other thing you can do is actually just put a hot filament near the sample, generate fermionic electrons, and the sample itself will determine whether it attracts or repels those fermionic electrons.
Oh,
and you only need a couple of volts to do charge neutralization that way.
really? I did not know that.
Right?
Yeah, it makes sense.
Yeah.
Makes sense.
You just have to get electrons to or from the sample.
Yeah, that makes a whole lot of sense.
So
It doesn't affect the electric field at all that when as you're coming down the column.
You put only a couple of volts on it.
Oh, cool. A few volts, not hundreds of volts.
2 or 3 volts
Huh.
negative, and that's enough to attract electrons towards the sample.
Very interesting. Huh. Tell me more about I can actually do that in my chamber.
Yeah, just tungsten wire.
Cool. We have plenty of those, right? We got old tungsten emitter. I can steal an emitter from my little tungsten emitter. Cool. That's great. Yeah, we should definitely talk. I can see what we can create some samples for you. Because that's a really fun thing to do. That's basically, they did that for me multiple times when I was doing apps training. And I was like, this is awesome, but no one's going to do it because it takes too long. But it is very cool to see, right? It's a good teaching tool for sure. But it's also a really good tool if, if somebody was willing to do that.
That's in our SEM course. Well, we have two different courses, but there's different labs. So one that wanted to do a little bit is semiconductor lab.
That's a great idea.
That's nice having Maria here. I can give her the ideas of stuff to do, and she can work on them more as well.
That's great. Well, we'd love to help.
It'd be fun.
Cool. I'd also like to send my users to you guys. Because, again, like training people to use SEM that are not microscopists is a different kind of challenge, right? You're trying to train people to get good images and understand what they need, but maybe not necessarily understand all the things you're talking about now. So it's definitely a different kind of challenge for sure.
It's a synergy.
Yes, that's right. It's a synergy. So, all right. Do we have any questions online, or we?
I hadn't seen it online.
Good.
Okay.
All right.
Awesome.
Thank you all for coming. I really appreciate it. And again, I'm at Nanotech West. So if you have questions about this type of thing, or you want to talk about fabrication, I'm always there. Out on West Campus.
Thanks again.
Thanks.
Yeah, we do.